All right. Good morning, everyone. So let's begin. In the last class, we were discussing basic properties of information theoretic quantities. We talked about entropy, mutual information, and I also talked about the data processing inequality, which basically says that if you have three random variables which form a Markov chain, then the mutual information between the random variable in the middle with either one of these two is greater than or equal to the mutual information between the extreme random variables. And one way to look at this is that if you have, you can view this as though you're passing x through a DMC to get y, and then you pass y through another DMC to get z. Then the mutual information between or the capacity of either one of these DMCs is going to be greater than or equal to the capacity of the effective DMC obtained by concatenating these two. And basically what the data processing inequality says is that no amount of pre-processing or post-processing can increase the mutual information between two quantities. So if you have a random variable x, which you want to say estimate or get some information about, and but what you get to observe is the random variable y, then if you post-process y to get z, then then this post-processing cannot help in increasing the mutual information. The mutual information between x and z will always be less than or equal to the mutual information between x and y. Right? Of course, all of that it's only saying is that it only talks about the mutual information, but sometimes whenever you're doing estimation or decoding, you want to convert y to a more simpler form, and typically the kind of post-processing you should do should make sure that you don't lose any information when going from y to z. All right. So in this class, we'll talk about channels, and I'll give a proof of the converse part of the channel coding theorem. Recall that the channel coding theorem said that there exist encoders and decoders. So for any given discrete memoryless channel specified by the transition probabilities Py given x, you can construct encoders and decoders such that the asymptotic probability of error is vanishing in n, and the asymptotic rate is close to capacity. And today we are going to prove the converse part of this statement, which says that no matter what sequence of encoders and decoders you choose, no matter how you try to design these encoders and decoders, the asymptotic rate or the asymptotic fraction of information bits transmitted per channel use, if you try to operate at any rate above the capacity, then the probability of error is bounded away from zero. You cannot make it go to zero as n tends to infinity. So we'll prove this weak converse for the channel coding theorem. All right. So before we proceed, are there any questions from the last class?
Hello, sir.
Yes, sir.
Sir, can you please repeat that data processing inequality?
Okay. So the data processing inequality basically just says that, so you have three random variables x, y, and z, and they form a Markov chain, which means that conditioned on y, x and z are independent of each other. So the probability mass function of z given xy is equal to the probability mass function of z given y. Z given xy of z given x comma y is equal to pz given y of z given y. Yes, this holds for all x, y, and z. So if X, Y, Z form a Markov chain, then the mutual information between X and Y is greater than or equal to the mutual information between X and Z. And also the mutual information between Y and Z is greater than or equal to the mutual information between X and Z. Okay, that is exactly what the data processing inequality says. And of course, you can interpret this in many different ways. One way of interpreting this in terms of channels is that if you concatenate two channels, basically you take the output of DMC number 1 and then you feed this to the input of another discrete memoryless channel, DMC2, then the capacity of the effective channel is always going to be less than or equal to the capacity of either of these two channels. So IXZ is always going to be less than or equal to IXY and IYZ. That is one way to interpret this. The second way of interpreting this is that suppose that you have a random variable X and another random variable Y. So how much information about X does Y contain? Right? So that is IXY. Now the question is, can I post-process Y? So I do some kind of post-processing on Y to get some other random variable Z. Can I get more information about X from Z than I get from Y? So is it possible that IXZ, so the amount of information about X that I get from Z is IXZ. So can I do some kind of post-processing such that I can increase the amount of information I get about X? The data processing inequality basically says that this is not possible. The mutual information between X and Y is always greater than or equal to the mutual information between X and Z. Okay, and similarly, if I have X, Y, similarly, if I have this, can I do some sort of pre-processing such that the mutual information between U and Y is greater than or equal to the mutual information between X and Y? And it basically says that this is not possible. The data processing inequality says that the mutual information between U and Y is always going to be less than or equal to the mutual information between X and Y. Is that clear?
Yes, sir.
Okay. So we actually go to the proof of the channel coding theorem, there's one more important concept to discuss. Of course, we also saw the chain rule of entropy, which says that the joint entropy of X and Y is equal to h of X plus h of Y given X, and it's also equal to h of Y plus h of X given Y. Right? And similarly, there's a similar chain rule of mutual information. Now the question is, suppose I give you two channels, two discrete memoryless channels. How do you say that one is better than the other? And is it possible to sort of order these channels? Right. So one thing is, of course, if you have two channels, you can always say that. So if the capacity of DMC1 is greater than or equal to the capacity of DMC2, then the first channel is obviously better than the second channel. But later on, when we discuss broadcast channels, we'll need something a more stronger property than just two channels being one channel being better than the other in terms of capacity. Okay, so we'll use this notion of degradedness. So we'll say that given two channels, let's say that the first channel has transition probabilities QY given X, and another channel with transition probabilities PZ given X. We'll say that this channel is degraded with respect to this other channel if you can write. So basically I have DMC1, right, and I have another DMC2. So these are two channels. The input to channel number 1 is X, the output of the channel is Y. For DMC2, let us say that the input is X and the output is Z. Okay, so we'll say that DMC1 is degraded with respect to DMC2 if you can effectively write this transition probabilities as though it is a concatenation of two other DMCs. So DMC3. So basically, if you can write the transition probabilities Q Y given X as that obtained by the concatenation of DMC2 with some other channel, then we'll say that this is degraded with respect to this channel. R Y given Z. So if it is possible to write one particular DMC as the concatenation of the other DMC with some other, if it's possible to find a DMC3 such that DMC1 can be obtained as a concatenation of DMC2 and DMC3, then we'll say that DMC1 is degraded with respect to DMC2, right? So what can you say about the, okay, so before we proceed, is this concept clear? Is the definition of degraded channel clear? Okay. So now, what can you say about the capacities of DMC1 and DMC2? Is one greater than the other? Is one less than the other? Or is it not possible to say anything in general?
Capacity of DMC2 should be greater than capacity of DMC1. Then only we can say that DMC1 is degraded with respect to DMC2.
Correct. So we have this equivalence, and the claim is that the capacity C DMC2 is greater than or equal to C DMC1. In fact, I claim that the mutual information between X and Z is greater than or equal to the mutual information between X and Y, and this holds for all input distributions Px. Okay, so note that the capacity is also a function, so it's obtained by maximizing the mutual information. In particular, it is obtained for some input distribution. Some input distribution will maximize this, will maximize this mutual information, and some other input distribution may maximize this particular input distribution. So firstly, why is this statement true? Why is the mutual information between X and Z always greater than or equal to the mutual information between X and Y?
So it's a kind of data processing inequalities follows.
Exactly. So note that you are obtaining Y. So basically you can write Y as though it is being passed, as though you are passing Z through another DMC. So this means that conditioned on Z, X and Y are independent. Right?
Sir, shouldn't it be okay? DMC1 here we are saying that after passing X to DMC2 and then DMC3, after that we get Y. That whole thing we are representing DMC1.
Correct. So the transition probabilities of the effective transition probability between X and Y. So when it is obtained by concatenating DMC2 and DMC3, this is the same as DMC1.
Yes, sir. Yes,
Okay.
I got it. Thanks.
Okay. Fine. So therefore, you should convince yourself that X, Z, Y form a Markov chain. And now you can use the data processing inequality to argue that the mutual information between X and Z is greater than or equal to the mutual information between X and Y. Okay, but what you have to note is that this, at least it is not obvious from this, that the capacity of DMC2 is greater than or equal to the capacity of DMC1, because the Px which maximizes this mutual information need not be the same as the Px which maximizes this particular mutual information, right? Because the capacity achieving input distribution for DMC1 could be different from the capacity achieving input distribution for DMC2, right? So I leave it to you as a homework to properly argue that even that if this is greater than this, then the maximum of this is also greater than or equal to the maximum of this. So show that the capacity of DMC2 is also greater. So this implies that the capacity of DMC2 is greater than or equal to the capacity of DMC1. Okay. So to understand this, let's look at some examples. Okay. So let us look at the binary symmetric channel. So recall that the binary symmetric channel can be described as follows. The input alphabet is 0, 1. So at the input, you can either transmit a 0 or a 1, and at the output you'll also see a 0 or a 1. The probability of observing a 0 at the output, given that you transmitted a 0, so for the BSC P, is 1 minus P. So basically whatever you transmit is received without any error with probability 1 minus P, and the probability of a crossover, that is the probability that a 0 becomes a 1 or a 1 becomes a 0, is P. So this is the bit flip probability. Okay, so you transmit a bit, you receive another bit. The probability that the bit gets flipped is equal to P, and the probability that it is received as is 1 minus P. Okay? And now you want to know whether BSC 0.1, so the BSC with crossover probability 0.1 is degraded with respect to BSC with crossover probability 0.2, or if the BSC 0.2 is degraded with respect to BSC 0.1 or not. Okay. Okay. So which one can be degraded with respect to the other? So firstly, what is the capacity of BSCP? Do you recall what the capacity of the BSC is?
1 minus h of p, I guess.
Correct. So it's 1 minus the binary entropy of P, where we define this binary entropy as minus P log P minus 1 minus P log 1 minus P. Okay, so this is the capacity. So what can you say about the capacity of the BSC? So as you increase P, what will happen? So even before that, so let us just look at the binary entropy of P. Do you remember what this curve looks like? So P varies from 0 to 1. So from
Increase. It is straight line crossing
is,
through 0.
so will it increase from 0 to 1?
Yes, increasing.
Okay, that's not true. So we're looking at the binary entropy of P.
So it will
Again,
decrease from 0 to, like, it will decrease from 0 to n. It will be 0 at half. If you,
Yeah, okay.
and then it will be
okay,
increasing.
you're talking about the capacity,
Downward,
right?
Yes, sir. Yes, sir.
So okay, fine.
downward,
But
Downward
if you,
parabola, like.
yes, so but if you look at the just the entropy, then it will be
Yeah,
downward
increasing.
parabola.
downward parabola.
Correct. So the entropy will be an upward, it will be kind of parabolic.
Yes.
And if you plot the capacity versus P, then it will be downward parabolic.
Yes.
It will be equal to 0 when P equal to a half, and it's equal to 1 when P equal to either 0 or half. So it's symmetric about half. And that's intuitive. When P equal to 0, then you know exactly, when P equal to 0, then it is not flipped at all. So so there's no uncertainty in the output given the input. Again, when P equal to 1, then you know that you're going to get it exactly flipped, and there's no uncertainty in what was transmitted. So if you transmit a 0, you know that you will get a 1. If you transmit a 1, then you know that you will get a 0. Right? So in both cases, the capacity is equal to 1 bit. Okay, so the first question is, so is the BSC 0.2, is this degraded with respect to BSC 0.1? So can the BSC 0.1 be degraded with respect to BSC 0.2? Can the BSC 0.1 be degraded with respect to BSC 0.2? Is that possible? Can BSC 0.1 be degraded with respect to BSC 0.2? So once again, recall the definition of degradedness. So DMC1 is degraded with respect to DMC2 if you can effectively write DMC2 as the concatenation of DMC2 with some other DMC, whatever that may be. Right? So I claim that this is not possible.
Capacity of DMC2 should be greater than capacity of DMC1.
Exactly. So this is not possible because the capacity of the BSC 0.1 is greater than the capacity of BSC 0.2, so it cannot be degraded with respect to BSC 0.2. Now, of course, the capacity of BSC 0.2 is greater than the capacity of BSC 0.1, but that doesn't necessarily mean that it is degraded with respect to BSC 0.1. So let's check. So suppose that we take two binary symmetric channels. Okay, so this is the first binary symmetric channel. Let's say it's a BSC P. minus P. Okay, so this is the first BSC, and then I concatenate it with another BSC. Okay, so I take the output of the first BSC and then I feed it to the input of another BSC. So 1 minus P prime, 1 minus P prime. So basically I have one BSC. Let's call it BSC P. I feed the output of this to another BSC P prime. Okay, and let us see what the effective channel is. Okay, so suppose that the input is X, output of this, the first BSC is Y, output of the third BSC, the output of the second BSC is Z. Okay. Now, what can you say about PZ given X of, let's say 0 given 0? What is this equal to? The probability that Z is equal to 0, given that you transmitted a 0 at X.
One minus P into 1 minus P dash.
1 minus P into 1 minus P dash. Is that it?
Plus
Plus some
P into 1 minus P dash.
Plus P
P
into
1 minus P dash.
usual is 1 minus P dash?
No, sir. P into P dash.
Correct, P dash, right? So what can happen is that you transmit a 0, then Y is 0, and therefore Z is also 0. So it is 1 minus P into 1 minus P prime. Or what can happen is that you transmit a 0, at Y it's equal to 1, but then it gets flipped again to give you a 0. Right? So either there are no bit flips at all, or there are 2 flips. Right? So both of these give you a 0 at the output.
Oh, I think, sorry. In the input side of X, we have written as 0 and 0 at the top and bottom side.
Okay, sorry.
Sorry, I got confused. I just saw the numbers.
Yes. So this is the one. My bad. Okay. So similarly, what is PZ given X of 1 given 1? So you transmit 1 at the input and you get 1 at the output of the second BSC.
Same as that.
1 minus P into 1 minus P dash.
Correct.
Yes.
P prime. So it's the same, right? Now what about P Z given X of 0 given 1? You transmit a 1, but then you receive a 0 at the output of the second BSC.
P into 1 minus P dash.
P into 1 minus P dash.
1 minus P into P dash.
1 minus P into P dash. Okay. What about PZ given X of 1 given 0?
So, P into 1 minus P dash, same, I think.
This is the same, right?
Yes.
1 minus P dash plus 1 minus P into P dash. Okay. So what is the effective channel? What does it look like?
Sir, it look like another BSC with
Exactly.
conversion probability P into 1 minus P dash plus 1 minus P into P dash.
Exactly. So the effective channel is basically another BSC X Z. So this is 0. Where the transition, the crossover probability is P into 1 minus P prime or P dash plus P dash into 1 minus P. Right? So the concatenation of two BSCs is another BSC and with some other crossover probability. So what can you say about this crossover probability? Is this greater than P? Is it greater than P dash, or is it less, or can it be anything?
It would be less than that. That's it.
Can it be less?
Maybe.
So think about it
No.
logically. What could happen?
No, sir. Let me.
So okay. So now is this channel degraded with respect to this channel?
Sir, it depends upon the conversion probability.
Okay, but for anything, so as long as P and P prime are greater than 0, it's between, suppose that between 0 and half.
So according to the inequality, it has to be degraded, sir.
It has to be degraded, right?
Yes.
So therefore, so I'll give this. So the claim is that P into 1 minus P prime plus P prime into
If
1.
P is less than 0.5 and another is greater than 0.5, I think it might increase. Is there any chance like that?
So you're saying that if P is greater than 0.5 and
another one is less than
0.5, my claim is that no matter what, okay, so it's a little more nuanced than that. So we'll see what happens in just a minute. So I just want to introduce one sort of notation over here. I'll say P star P dash is this quantity, P into 1 minus P dash plus P dash into 1 minus P. Okay. Now let's look at P star P dash is P into 1 minus P dash plus 1 minus P times P dash. Okay, so let's look at let's look at P. Okay, so the capacity. So we want to know if P star P dash, what is its relationship with P? Okay, it doesn't matter what P is. P could be less than half. It could be greater than half, and we'll see what happens in both cases. Okay. So firstly, now let's look at this quantity over here. We have P over here and 1 minus P over here, right? So what can you say about the capacity of BSC P and the capacity of BSC 1 minus P?
They are same, sir.
They are the same, right? Because it's symmetric. So this is 1 minus h of P, and h of P is symmetric in P and 1 minus P.
Yeah, it is symmetric.
It is the same, right? So the capacity, okay, so it's going to look something like this, right? So you pick any P. Suppose if this is equal to P, then this is going to be 1 minus P. All right, so this is going to be, so both of them are going to have the same capacity. So it is 1 minus H2 of P. Okay. So this is the point, right? Now what can you say about P into 1 minus P dash plus 1 minus P into P dash? So P dash is some number between 0 and 1. Okay. So what kind of a function or what kind of a combination is this of P and 1 minus P?
It's a convex.
Exactly. It's a convex combination of, so P star P dash is a convex combination of P and 1 minus P.
Yes.
All right. So So basically, since it is a convex combination, it is obviously going to lie somewhere in between P and 1 minus P. You agree?
Yes, sir.
Exactly.
Yes, sir.
So it's going to lie somewhere in between P and 1 minus P. So therefore, if so this is assuming that P is between 0 and half. So if P is between 0 and half, then no matter what P prime is, so for any P prime between 0 and 1, this P star P prime is going to lie somewhere in between P and 1 minus P. Okay, because it's obviously a convex combination. So my P star P dash is going to lie somewhere in between. And since the capacity is a convex function of P, the capacity of the effective BSC, the capacity of BSC P star P dash is going to be less than or equal to the capacity of the BSC P, right? Now, even if P is greater than half, so suppose that this is equal to P, so P is between half and 1, then 1 minus P would be between 0 and half, right? And still, so in that case, for every P prime, P star P dash would lie in between P and 1 minus P. So it would be less than P, right? But the capacity would still be less than the capacity of the BSEP. Okay, so therefore, the capacity of the BSC P star P dash is going to be less than or equal to the capacity of BSC P. It's also less than or equal to the capacity of BSC P dash. Is this much clear? Any questions? Okay. So therefore, the BSC P star P dash, which is obtained by concatenating a BSC P and a BSC P dash, so this is degraded with respect to either of these two channels. Okay. All right. So now let's look at the original question. Our question was: is the BSC is BSC 0.2 degraded with respect to BSC 0.1? So this was our question, right? So is it possible to write the BSC 0.2 as a concatenation with BSC 0.1 with something else? So this effectively boils down to asking the following question: can this be written as P star P dash, where this is our P? Right? So basically, you have to find a P dash such that you can write this as P dash times 1 minus 0.1 plus 1 minus P dash times 0.1. Correct? So all you have to do is just solve and see if you can get a P dash between 0 and 1. So can you solve and tell me what P dash should be? Okay, fine. So So it says that it is 0.125.
Yes, 1 by
So
8.
0.125, right? Okay. So basically a concatenation of so BSc 0.2 is indeed degraded with respect to the BSc 0.1, because you can write BSc 0.2 as concatenation of BSc 0.1 with BSc 0.125. Right? And note that it doesn't matter in which order you concatenate, right? So I can write the BSc 0.2 as concatenation of BSc 0.1 and BSc 0.125, or concatenation of BSc 0.125 with BSc 0.1. The order does not matter because this quantity is symmetric with respect to P and P prime. Okay, so that is fine. So that was the BSc. Now let's look at the BEC. So the BEC has input alphabet 0 and 1. The output is either 0 or 1, or it's an erasure symbol. So whatever bit that you transmit gets erased with a certain probability. Let's call it P, the BECP. And it is transmitted as is with probability 1 minus P. And the capacity of the BECP is 1 minus P. So you should go back to your information theory notes and see how we derive the capacity of the BEC and the BSC. So try to maximize the mutual information with respect to all input distributions, and you should be able to show that the capacity is for the BEC is 1 minus P, and for the BSC it is 1 minus H of P. All right. So this is for the BEC. The capacity is 1 minus P. So now, so what does the capacity look like as a function of P? So this is P, varies between 0 and 1. This is the capacity. What does it look like?
Passing
A straight
through
line
1,
passing
0, 0,
through.
1.
Correct. So it's just a straight line, just monotonically increasing from 0 to 1. Sorry, monotonically decreasing. So when P equal to 0, the capacity is equal to 1. You can transmit everything. And when P equal to 1, basically everything gets erased. So the capacity is equal to 0. Right? So it's a decreasing, it's a straight line, which is monotonically decreasing from 0 to 1. Okay, so obviously the BEC 0.1 cannot be degraded with respect to BEC 0.2, but it's possible that the BEC 0.2 may be degraded with respect to BEC 0.1. All right. Okay. So let's look at the concatenation of two BECs. Of course, now you can't, right? So this is an erasure, 0, 1, 0, 1. Right? So we want to know if BEC 0.2 is degraded with respect to BEC 0.1 or not. So we can't use the same approach, because if I call this X, if I call this Y, then I need to construct another channel from Y to Z, whose input alphabet is 0, erasure 1, and output alphabet is 0, erasure 1. Right? So what kind of a channel do you think we could choose? So I basically what I want is that the effective channel from X to Z should be another BEC. So how would you construct such a channel?
One BS, so two BSCs between 0 and erasure, and one more BSC with erasure and 1.
I guess you mean transitions from
Transitions.
so 0 to erasure, 1 to erasure, and then from
No,
0
sir.
to
What I mean to say is from
okay.
0 to 0 and 0 to erasure, it will be like a normal binary symmetric channel.
It's
There are two different binary symmetric channels between 0.
You mean like this?
Yes, sir.
Okay, fine. So you want this, and then you have something like this, is it? This is what you
Yes, sir.
want to construct? Sure. So
Yes.
so of course this is certainly possible, but there's probably something easier you can do. So the following will make your life easier, and that is you just so we put another erasure channel, and from the erasure to the erasure, you keep it as is. So with probability 1, an erasure remains an erasure, but the 0 could potentially become an erasure. So let me call this P prime, 1 minus P prime, 1 minus P prime. So the example you gave could be perfectly valid. And so you can try to find out what is the corresponding values of the transition probabilities, which will give you an effective erasure channel, right? But this will probably make calculations a little simpler. Okay. So now what is the probability Pz given x of 0 given 0?
One minus p, 1 minus p prime.
1 minus p into 1 minus p prime, okay. And similarly, pz given x of 1 given 1 is also 1 minus p into 1 minus p prime. Now, what about what we really want is what is the probability of z given x, of what is the probability of receiving an erasure given that either 0 or 1 was transmitted, right? So, what is this equal to?
1 minus p into p prime.
Prime
And plus p.
Plus p, right? And this is the same as, so pz given x of erasure given 1, right? So basically the concatenation of these two channels is another BEC. So what is the effective channel? It's still a BEC, right? So it is a BEC 0, 1, 0, 1. E, and the probability of an erasure, so this is a B, let me call it P double prime, where this is my P double prime. So P double prime is 1 minus P into P prime plus P. Okay, or this is equal to P plus, yeah, so it's okay. Let me keep it this way. So it's clear that this quantity is obviously going to be greater than or equal to P prime. Sorry, it's greater than or equal to P, right? Because after all, this quantity is non-negative. 1 minus P into P prime is going to be greater than or equal to 0, and therefore this entire quantity is going to be greater than or equal to P. So obviously this is degraded, and it's strictly worse than the capacity of, or it's strictly worse than the BECP as long as P prime is greater than 0. Okay, so to show that the BEC point 2 is degraded with respect to BEC point 1, sorry, BEC point 2 degraded with respect to BEC point 1, you basically need to find out what is the P prime which converts a BEC point 1 into a BEC point 2. So my P double prime is 0.2 and my P is 0.1. So you just need to find the P prime for which you get 0.2, 0.1. Okay, so I'll leave this.
1 by 9.
It is 1 by 9, is it? So this is equal to, so P prime is equal to 1 over 9. Okay, that's good. All right. So, okay, so I leave the last part probably as an exercise, but here are two things you should check. So first, a BSC point 1 versus a BEC point 1. Okay, so you have to check what is the capacity of the BSC point 1 and the BEC point 1 and which can be degraded with respect to the other, and try to find out how you can convert one to the other. Okay, so try to solve this and also try to solve the following. So BSC 0.01 versus the BEC say 0.5. Okay, so see if it is possible to show that one of these are degraded with respect to the other or not. Okay, now what about AWGN channels? This is much simpler. So AWGN sigma 1 square versus AWGN sigma 2 square. So if sigma 1 square is greater than or equal to sigma 2 square, then what can you say? Can you say that this is degraded with respect to this?
Sir, where sigma square implies noise power? Or
Yes. So sigma square is a noise power. Let me be a little more clear. So the channel is basically X, additive noise. Let me call this W1, which is Gaussian with mean 0 and variance sigma 1 square. Output is 1. Okay, so this is my AWGN channel with noise variance sigma 1 square. There's of course a power constraint, but the power constraint, let's assume, is the same for both channels.
So then one is degraded with respect to 2.
Correct. So the first one is degraded with respect to 2. And this is probably more intuitive and more obvious, because what happens if you concatenate two AWGN channels? So suppose I have this channel. This is Gaussian with mean 0 and variance sigma 1 square. And I feed this to the input of another AWGN channel with mean 0 and variance, let me call it rho 1 square. So what is the effective channel going to be?
Another AWGN with
Another AWGN.
Sigma 1
Summation
square
of
plus
variance. Sigma 1 square plus rho 1 square.
Yes.
So if you have two Gaussians, independent Gaussians, then the sum is also going to be Gaussian, with the mean being the sum of the two means, and the variance is going to be just the sum of the variances. Right? So this is the effective AWGN channel. Right? So this is obviously more natural, and it's obvious that this is that if the variance is larger, then it's going to be more degraded with respect to another channel with a smaller noise variance. But what if the noise were not AWGN? Okay, suppose that let us say that, so look at two channels. Let's call it the U channel. So U for uniform, where the noise, so the input is X, the output is Y, both being real numbers, and the noise is uniformly distributed between, let's say, minus alpha to alpha. So this is a U alpha channel. Okay. So if you look at U alpha 1 and U alpha 2, okay, where alpha 1 is greater than or equal to alpha 2. All right. So if I concatenate two such U channels, will the concatenation be another U channel? If I take two independent U channels, is the concatenation going to be another U channel?
May not be, sir.
May not be or will not be?
It will not be, sir. Means if we use the basic of central limit theory, then if we
Look,
use,
central limit theorem is for a large number of
yes, sir, yes, sir.
variables, right? But even more. So what is the concatenate? What is the okay? So basically, if I concatenate two U channels, so suppose that this is W1, and then I have another W2. W1 and W2 are independent, and both are uniformly distributed. The first is distributed over 0 to alpha 1, the second from minus alpha 1 to plus alpha 1, and this is uniformly distributed between minus alpha 2 to plus alpha 2, right? So this will be effectively some channel with additive noise W, where W equal to W1 plus W2. So what can you say about the PDF of W?
It will be varying between minus alpha 1 to alpha 1.
Are you sure?
Here we are mentioning that like alpha 1 is greater than or equal to alpha 2. So it should be varying between alpha 1, minus alpha 1 to alpha 1.
My claim is that it's going to be even beyond minus alpha 1 to alpha 1.
Yes, it's alpha 1 plus
Kind
alpha
of
2.
step, 2 steps it will be, right?
2 steps. So if you have two independent continuous random variables, then what can you say about the PDF of the sum of those two random variables?
It's a kind of adding to square functions.
Sir, it's convolution.
Convolution.
Correct. It's the convolution, right?
Yes.
Yes.
So FW is going to be the convolution of FW1.
Sorry, then it will be triangular waveform, I think.
Exactly. So it's going to be a triangular wave. And what is going to be the range of W?
So sum of lower limit and sum of upper limit will be.
So minus alpha 1 minus alpha 2 2
lower
alpha 1 plus alpha
alpha
2.
2.
So it's going to be like a kind of like a triangle.
Yes.
Not exactly, because because alpha 1 could be different from alpha 2. Right? Sorry, no, it is going to be triangular.
Range may be different, sir, since alpha 1 or alpha 2 are not same, I think.
Correct. Alpha 1 and alpha 2 are not the same, yes.
But the shape is triangular. It's
So it won't exactly be triangular. It will probably look something like this. So it'll increase,
Trapezoid.
and then it will remain constant for a while, and then it will again decrease.
If both are not equal, alpha and alpha 2,
When they're not
that
equal,
equal.
yes.
Yes,
Then it will
If
be
alpha 1
trapezoid.
equal to alpha 2, then it will be a triangle. But then if one is strictly larger than the other, then it will look like a plateau.
Yes, sir, trapezoid.
All right, so let's stop at this point. So that's what. So refresh the capacity of the BSC, the BEC, and the AWGN channel. And before the next class, try to also solve these problems that are there. So whether the BSC 0.1 is degraded with respect to the BEC 0.1, and BSC 0.01 is degraded with respect to BC 0.5, or the other way around. So whichever is compatible. Right? Any other questions? Okay, so if not, then we meet in the next class on Wednesday.